Okay, so we will continue from our previous lectures. Okay, we talk about the simplest inverter, that you can actually do it yourself, which is called the AC push pull, DC to AC, push pull topologies. I say this method have a two problem. One is that you will never get a sine wave. So this leads to a very high total harmonic distortion of 40%. Now, like I said, if for a standard, what we call a good inverter, your THD should be less than 5%. This is quite worldwide standard, I would say. Malaysia TMB also set it as 5%. IEEE standard also set it at 5%. But why it still can be used? Like I said, it is off grid. You are not connected to the grid. And then secondly, it's limited to a very low power application, so it doesn't really matter. Now, if you are designing a very high power, my high power means like 1,000, 2,000, or 10,000 watts. That's high power. And if you have more than 5%, let's say 6% of harmonic, what will happen to the load? The load will actually overheated. Due to this harmonic. That's why for the grid connected, they do not allow anything more than 5%. But low power, never mind. 100 watts, not much heat it can generate unless you connect straight to a heater. So that is the reason why it's still applicable. In many what we call low power application. Like I said, it has a disadvantage of high harmonic voltage and current. And then of course it's huge and heavy. As the power increases, right? If you want to design a 1,000 watt, right? Most probably, the inverter size is going to be like my laptop area already. 1,000. That big, and it's very, very heavy. I think 10 or 20 kg because of the transformer itself. So that's why it's not commonly used to for those high power application. Now, when you talk about high power, so the other types of topology will be commonly used. So one is what we call half bridge topologies. Now, half bridge or full bridge, they no longer use any transformer. Like I said, the transformer, provides step up, but the problem is that the higher the power it is, the more heavier it is. So now it relies on only two transistors, still the same two transistors, right? But they connect in a way that, one is on top, one is at the bottom, and this is what we call a half bridge. And then connected to a DC source. The trick is you need two capacitors, You have to use two capacitors connected in series so that the center tap here of the capacitor will act as a neutral ground. Will act as a neutral ground if you want to use this half bridge topologies. So how it operates, very simple. This will be the output point and then connect to the neutral point. And when the top transistor is turned on, so you can see that it will go through here and then pass through here. Because this is turned off, it cannot go all the way to the ground. And it will pass through the load and to the center tap ground. So you will have a positive here and a negative here. That will give you a positive cycle. And then the next cycle, you switch it at the bottom, and now this is on, and this is off. And you can see that because of the capacitor, it has been charged, right? It has been charged. Okay, so the positive is here, the negative is here. So it relies on this capacitor to discharge through here, but you can see the sign different already, plus, minus, now the plus and minus, right? The sign is different right now. So by doing that, you're actually creating a negative cycle. And you repeat the process, okay, this is what happened. Okay, on, off, and then you go on. You create, okay, an alternating, okay, output. All right. So a very simple concept. And now you actually removing the what we call the heavy component, okay, from these topologies. Now, again, as we know that it's still a square wave, right? So we will have this harmonic problem. All right. Now there are some basic equations to actually calculate, okay, the RMS value of the fundamental component. Since it is a square wave, okay, so basically it's VDC divided by 2, okay, multiplied by 0.9. That will be your approximate VRMS output. Okay, I will say approximate VRMS. Now, why the VDC need to be divided by 2? Because of the 2 capacitor. Because of the 2 capacitor. Now, if my DC voltage is 400 watt, this capacitor you connected is 400 watt, right? 2, but it has 2 pieces. So that it will divide by 2. The top one will carry 200 watt, and the bottom one will carry another 200 watt. Okay, and the voltage is actually serial, and you add up, it will be equals to the total DC voltage of 400. But when we producing the AC output, like it take the first half and the second half. Therefore, the VDC has to be divided by 2. Okay. Now, total harmonic distortion is actually the sum of the harmonic order. So if you really want to calculate this very accurately, like it is going to be a very lengthy process. Okay, you have to calculate the fundamental voltage and you sum all of them. If there are 20 order, you have sum 20 times, right? Not logic lah. I mean, we are not going to do it on paper. And then of course, the total harmonic distortion will actually decreases along the harmonic order increases. Okay, like we have shown in this one, you can see this is a trend. It will decreases. So people will start to work out on a simplified equation, which is only applicable, okay, to square wave. So basically, THD, okay, is equals to 0.4359 divided by the magnitude, which is 0.9. Okay, then of course, if you cancel this off, right, regardless of the VDC, you just take this one, divide this one, you will get the THD output. So again, it's around 40% plus. Okay, so it's very similar to what we simulate. Okay, later we will try in the simulation. So these are the 2 things, because it's still not sine wave, nothing much to calculate. But these are the basic fundamental. Okay, now when we come to implement this, okay, now my VDC, I put 500 watt. Okay, so we will have 250 here, right? 250 watt, 250 watt. And then we will create a ground or neutral ground in the middle, where your neutral ground is connected to your solver. And then we have to place 2 transistors. Okay, and then we will place this 100 ohm resistor load. And we will switch them with a pulse generator. And remember, do not turn on both transistors at the same time. It causes short circuit and explosion. I mean, when you are building the real hardware. In the simulation, it's safe. Okay, but this is very important. That's why you can see that the output of this, again, I have a NOT gate here. So the NOT gate will eventually, okay, invert, okay, this one, okay, become like that. So that they will never be turned on at the same time. Now, the 5 volt here is the threshold voltage of your transistor. Remember, we have the threshold voltage, otherwise it will not turn on. And then at the, what we call this output here, we measure the voltage. And then there is a block called THD. It will calculate the THD for you. Okay, it will calculate the THD for you. And then there is another RMS block. Okay, so from here, when you simulate, okay, again, you can see it will produce, okay, the square wave. This is the signal generator lah. Okay, it will be the same as the one you used, okay, previously. All right, these are the setting of the RMS and the THD block. Make sure to change the frequency to 50 Hertz because MATLAB is from US. By default, they're set to 60 Hertz. And check this specified harmonic. So it will calculate the harmonic number, which is harmonic 1, the first harmonic, which is the fundamental harmonic for that distortion. And then for RMS, again, is also we set to 50 Hertz. Now, if everything okay, right, you should be able to produce a sine wave, okay, like that, which will have a, what we call a, like I show here, okay, 227 volt RMS, quite near to our 230, and a total harmonic distortion of 45.85%. Okay, let's run it here, okay, which I already have made this. Okay. Okay, so if we run this, okay, so of course this will be the output. Okay, this will be the output. All right, and RMS. Okay, RMS measurement blocks. And we calculate again at the first harmonic, THD, 50 Hertz. The rest is more or less the same, okay? So again, yes, please do that, okay? I think the value I already put here, okay? All the necessary setting, okay, is inside the slide. And the transistor I use, if I'm not mistaken, is, okay, is this one, the MOSFET. I think I use this one, ideal switching. Okay, I use the ideal switching. Okay, so we don't do any setting, we just plug in the MOSFET. So it's important for initial design. When you design any inverter, right, you don't care about the transistor detail first. You drag in, you make sure it's switched properly, okay, done, confirm, only then you want detail, right? Then you only put in the detail transistor. And I think the rest is, okay, wait, control, transform, measurement. Okay, so from here, right, you go to control and measurement, you can find the THD and the RMS measurement is inside here. There are a few RMS, but this one's supposed to be better. electrical, right? Scheme-scape, electrical control under measurement. So you can have this, you know, RMS and this total harmonic distortion. So it automatically calculate for you in percentage. So you just drag all on here, like that, okay? Then double click, you know, and then you remember to change the frequency, okay, to change the frequency. So 1 to calculate, and then you will see based on the equation here, right? So what you get from this 0.4359 divided by 0.9. And you see, is it close to this value you get in the simulator? Okay, to this value, all right? Okay, so please do it now. And then, yeah, screen capture and paste it, okay, when you are done. And remember to keep this because later we're going to have full bridge and then we move on, you know. Otherwise, later when we come to the grid inverter, it's going to be chaos for you. I know it's going to take some time, okay, especially first timer to do this. But when you are familiar enough or this simulating, it is going to be very fast lah. I hope today we can finish the full bridge. And then after CNY, we come back, right? We will go through the filtering and the grid connector. You guys are working on it, right? Hello, online one?
Yes, sir, doing now.
This is only single phase. If you come to three phase, yeah, as you can see in my note, right, we also talk about three phase. So it becomes more complicated. But of course, there are simplified blocks to make the design much more easier. Then later I will continue on. But as for the fundamental, we need to do it at the transistor level. Because if you straight away use the block, right, for simulation is okay. But if one day you really want to implement the hardware, then it will be a problem. Yes.
May I know what is this?
This is a NOT gate.
Not yet. But
Yeah.
When we switch the not yet, it's not showing in this.
It's here. Okay. Okay, it's under logic The very first one, Simulink, logic, and then you go all the way. Now you don't find the NOT gate. Why? Because it is the logic operator. So you have to drag it here. You see, when you study digital, right? There's AND gate, OR gate, whatever gate. So Simulink don't create all of them. They create one. Let's say this is the AND gate, right? You double click. You actually can change it to NOT gate. You click here, then done.
The logic bit operation is it?
Yeah lah. Wow. Is it because of New Year Eve or this is a bit too complicated for you guys? Because the past few classes, those online one will be pop up already. So Osama, can? Okay. Because what you showed me just now, you're using the specialized power system to do it. Okay, I mean, the principle is the same. It should work, okay? But because of this, I'm more focused about the real transistor right now, so we will use this one. Yeah. So try to visualize with this one because I'm working on your assignment right now. Currently, I was thinking to make your guys design a grid connected inverter as your assignment. Okay.
The holding model down now, checking some answer already. Something is here, but then I'm going to run under the error message. Suddenly, this converter wants to signal double. But what I expect is referring to this one. This is number one, converter number one. Apparently, it's getting an input signal of a double.
Wait. The problem is here.
Oh.
Okay, let's see. Okay. Okay.
Same as your one.
Same, huh?
Yeah. Non-block is also the same.
Not is also same, huh?
Logical operator not.
Yeah. This one?
Setting same.
Same.
Exactly your slide settings. 1 over 50, 50, 0. 1 over 50, 50, 0.
Okay.
Time-based simulation time.
Okay, click OK. The output is double with
Yeah. Okay, Boolean. Okay, now.
no, it's something wrong with that. As long as you have this number here, right? If something is wrong here, okay.
Which one? Same number as your one. Same number as your one.
Okay, threshold. Are you guys having the problem of number, right? All this number thing, right? You're using 2021. Okay, B.
Yeah,
A or B?
A.
A, yeah. Okay, this is a format problem. I don't know why it happened here. It doesn't happen on my side. Okay, let's see. The output is double, and then
All this Boolean.
All this Boolean. Okay, one of the possible solution to the problem you have here is that is the format not correct? Okay, they are Boolean and double, right? Okay. I don't know why it happened on your side. Okay, in case it happened, we will usually use a signal attribute to solve it. Okay, signal attribute, you will have this data type converter here. Okay, this is the data type converter, and then you drag it down. Okay, okay, because you have to find out what is the root cause of this. Maybe let's say example, if the root cause is because of the NOT gate output, that changes the output to become Boolean here, right? Okay, and then the transistor cannot accept Boolean. So we will put a converter here in this two, and you double click. Now you can change, okay, the data type output. Okay, so let's say, if you know that it needs a double, you just change to double here. That's it, whatever Boolean or whatever come in here, right? After this converter, it will change to a double. I'm not sure it's double or not, but I just guess because. Okay, maybe I will change here and see. If I put double, double.
Running now.
Okay, on my one can run if I change to double. Yeah. Can you sit back to your seat? Thank you. Okay, this is a very important knowledge of this Simulink. Because in Simulink, right, when later we come out with a lot of different PI control, whatever, so the output may be different format. It can be like a single or double or integer 8 or whatever. It's okay. You connect them first. Now, once you run it, it refuses to run, right? It will show you like the problem. It will highlight, oh, this is double, this is this. Then when you see this type of error, it means that the data format is not consistent. So that you will require to have this double or whatever to make it work. Okay, of course, you have to find the root. If the root is this one, you just need one double that will solve everything. If the root is here, then you need to have two, what we call the data format, okay, conversion. Let's see. Can or my one, is it I did something change somewhere so that I can avoid this problem? Okay, this one I don't change, everything same. Okay, this is also Boolean. Oh, you can also change it here. You see, when inside the what we call this gain, right? You see what we just set 5, then we click OK. But you can see you can change the attribute here. You can change double, built in already. Yes.
How do we find this?
Ayo, when I explain it, you will never listen
But forget already.
Okay, please don't ask something that I already explained, okay? You are showing me, sir, I don't listen to you just now. I don't like it.
Okay.
If something like this guy Ryan is asking, which I never explained in the class, I'm very happy to answer. Okay? Okay, this one, you have to go to, you see, in the record video, I explained this 2 times. Okay, you have to go to Simulink, electrical, control, measurement. It's inside here. RMS, THD. Okay, you guys try to change the attribute of this to, I think should be double this one. That's why doing yourself is very important. If you just copy and wait things to be happen, then you will not be able to do it next time. Okay, when no one is around. Oh, finally! Wow! Wow! So many output already. Okay. Let's see. Sir, why this kind of problem? Alamak. I think same lah. Yeah lah. Okay, same . Now you see, when you all have this error, right? Double and you see, unsigned fixed 8EN5. So it means that the transistor one is receiving double, the other one down here is receiving this format, which is not consistent. And this is caused by, these two. Okay, this logic operator. Like I said, from this one, you double click, you change the attribute to double, it should be able to solve. Okay, try to do it. I don't think so. It's the component problem lah. Ideal switching is correct. Okay, Lun Kung Wei, you try to remove the converter. Just change the one below to double C can work or not. Just double check lah. Because Okay. Oh, my friend, this one can work. Wk5.1, right? Oh, beautiful. Sama, finally, your one pop up. Can You see, this thing you really have to be update lah. Like I said, even I'm teaching this every year, and you know that lah. MATLAB upgrade 2 times a year, A and B, You know, even they have this built-in, I already like, wow, okay, how come I don't know? In the old days, we had to put the converter out there. But the converter is still useful because not all blocks come with the built-in. Okay, so maybe for some block, like for example, the pulse block, right? It doesn't come with built-in. Then you may need it one day lah. So this is just for your extra knowledge. So anyone here calculate the THD, see whether how much different from here. The one I show in the slide. This equation 0.4359 divided by 0.9. Calculate, see how close is it to the one that measure from the Simulink. The Simulink show, I think it's 45%, 45.8. I think 45.85. Yes.
One line look weird. It's supposed to be like that, but then this one is showing straight. And then my value is not showing.
Oh, you try to click this one, see, you are not seeing all of them yet. No, click this one.
This one.
Yeah. You see, the thing is that because the screen are so small, so every time you do this, right, the first thing to do is to click this one, so it swing everything. Like I say, you need to practice in the class so that you learn this.
But then my THD value is not showing me. It's supposed to be above.
Yeah. Then do you? Not yet finished lah. Still running. Aiyo, it's still calculating lah. Oh, that will depend on how powerful is your computer. A gaming computer with i7 usually very fast.
I think the runtime he set, then following a default runtime, he's supposed to set the runtime to 0.1, I think.
THD, you mean?
No, I mean the running time. When we press the run, right, there's stop time,
Wait. Sorry. There are people talk to me in the physical class. Wait. Let me. Okay, online one talk first. What is that?
Because why he running so long? Because the stop time he didn't change.
Oh.
You
see your friend. Online know what's problem. What is your problem here? You know why? Check your stop time. 10 seconds, right? You run until end of the class. Thank you. Okay, by the way, what's your name? Online?
Boon Hong.
Boon Hong. Hey, you guys should thank this fella, right? Boon Hong, okay? Ayo, Faiz. Don't behave like that lah. Hey, come on, alumni, you know, Chonghua fella, don't behave like that. No, it should be around this value. And then when we check with the calculation, it should be close enough lah, right? How much? 43? Oh, okay, yeah, 48, plus minus, yeah. That one is theoretical, okay? So if you look at this is around 45.85, 3% different, yeah. So you see, what this number tell you, okay, it is 50, apart from 50, right? So next time, when you look at the waveform, it's square wave, right? You can tell already, it's around 45 to 48. You will impress those young engineers, will say, "Wow, Sifu, how you know? Look at it, you know already, people need to buy this what we call fluke meter to measure, you know. That fluke meter is around 30 to 40,000 ringgit. And then that guy say, my eyes already meter. I look at it, I know already. So you don't be surprised. I mean, when you see those experienced engineers, sometimes they don't even need instrument, you know. They look at it, they know already. Okay, now I know what to do. So, you know, so it's important, you know. He may be running tons of simulation before and tons of this field experience. And as for us, young graduate, we were like, wow, how come you're so king one or something like that? No, nothing. It's nothing king. He may be one of the, like you guys here, doing this every class. So king. And those who never do that, of course, I even come out this with a final exam, ask them to calculate. They cannot give me the right answer. Because in my slide, right, you can see, I don't provide answer, you know, I just show this, right? I just show equation. And then I only tell you to calculate and match this one, you know. Then if exam say, I'll calculate a THD of a square wave, they look at the slide, where's the answer? What to do? Okay. Yes. Oh, so. Oh, you. Oh, double click this one. See, do you do the setting properly? Oh, this is interesting.
Also, I think it's division by zero error somewhere.
Division by zero error caused by you got the output or not?
The waveform, yeah.
Wow, interesting. Okay, it should be something to do with. Wait, okay, put this to 0. See. Okay, another new thing to learn. Okay, there are many blocks, right? They will have this sample time. They will have this sample time. It depends on the default setting. The default setting is -1, right? Okay. Now this means that -1 means inherited. Inherited, it will follow the whole entire simulation sample time base. Okay, so sometimes it works if the time base all matches. Now we are doing a lot of switching. They may miss a bit of this, what we call sample switching. So when this happens, right, it won't give you errors, but it just show you a 0. So to avoid that, we put 0. So we don't want inherit. So you will do a general calculation. So there are many blocks have this, like this one. You see, they have this sample time. And this one, usually those deal with timing one. If I'm not mistaken, this one don't have, okay. Deal with timing or measurement, they will have this. Even the display blocks have this as well. Okay, if you go this one, I think it's somewhere sample time. But this one inherit, okay, you can see the waveform. If no, you need to do some setting there. Okay, increase the sampling, or usually it's decrease. Usually it's decreased. Because you decrease the sample, right? It's easier for you to capture in the scope. Okay, it's just like, as we know that if we buy a real scope, right? The real scope got limitation, you know, how many megahertz or gigahertz, right? But this one we put -1 means infinity frequency it can measure because computer But because of the timing issue, it may not be able to measure. So we put 0. Okay. Okay. Wow. Okay, I think most people got it already. Oh, logic operator, I think you don't touch it. You want to change, you change the gain here.
Oh,
you don't cut
so
the.
I change with this so it can run smoothly.
Oh.
So I don't have the data conversion.
Oh, okay. Okay this is something flexible you can play around it Data type, okay. You see, my one is different because my one I think is old version. I'm not sure. Okay, I switch to Boland. Maybe you switch to this one can, yeah. Play around, the more you play around this, you know, the more you can make the thing better lah. Okay, so you can see even a very simple circuit like that, right? If you are not familiar enough, right, it's going to be very troublesome, and it will take you, you know, hours just to get it works. So it's again important to do it in a class session like that, so everyone learn from each other, including myself. I'm learning from you guys as well because you guys were exploring it. Okay. All right. So yeah, we need to move on already. Okay. So now we have done this. Okay. Half bridge. Now the problem with the half bridge is, okay, the pro first. The pro is simple. You just need 2 transistors. Okay, 2 capacitor done. But the problem is that you need 2 times higher the VDC. You see, we want to produce 230 volt. We need 500 of DC voltage. Not efficient, right? You need so high power. And then you also require 2 extra capacitor instead of 1 capacitor. Okay, but you only use 2 switches. Okay, the capacitor is to form a neutral line. So to solve this, they use 4 switch. Okay, 4 switch you can even ignore the capacitor. But okay, in practice they still put a capacitor to maintain the DC voltage. Okay, full bridge topology, okay, is the most commonly used in commercial inverter. Okay, Tesla, Powerwall, or standard grid connected, okay, they will use full bridge. Okay. And then half, you see, full bridge is just, you just need to have another half set, right? It will form a full bridge. Okay, so full bridge is pretty straightforward. So you can see that, okay, this one turn on, it pass here, come through here, and go. Okay, it will form a positive cycle. And the negative cycle, the other 2 turn on. Okay, again, the basic rule is that a single bridge, okay, will not be turned on at the same time, or else it will cause a short circuit, okay, to the DC source. So basically, it's just these 2, 1, 2, 1, 2, 1, 2, just like that. So now you already design the first half bridge, right? Cut and paste, copy to the second half. Okay, now the RMS equation different is, you can see down, the VDC is no longer required to divide it by 2. Okay, now just now you need to divide it by 2. Okay, because you need to double up. Now for the total harmonic resources is exactly the same. No change. Only this one different, the RMS value. Okay, so now you can still continue with your half bridge, right? Like I said, you just cut and paste this one, put it here, and you just connect these 2 lines. If the first one can work, this one guarantee work. But remember to change this to a lower VDC, change it to 250 instead of 500. Otherwise, you'll get a very high AC output. The rest is the same. Okay, the rest is the same. And then you will notice, right, the THD is now closer to the calculated value. Now, just now we calculate is 48, right? But the half bridge, okay, it gave us 45. Okay, a bit off but now it's much more closer. Okay, so full bridge is much more resemble a better switching. So, and then you can see, okay, it's around 225, okay, around 230. And the output should be more or less the same. Okay, so if we look at the oh, this one cannot. This one is a feedback control. Open the wrong file. full bridge. Okay. Okay, full bridge. So what you all have done here, just cut and paste, copy one another set. And the rest you just, connect. All right. Okay. And like I said, this is consider the topology that is widely used in the industry. Unless you got budget constraint, you say, oh, no money, I want to make my inverter cheap. Because the transistor, right, for high power is very expensive. Then you use the half bridge method. But like I say, practical, so far I see, all those commercial one, as far as I understand, they are all full bridge. Oh, okay, coming in already. Oh, piece of cake already, Good. That proves that you have enough practice. Okay, Osama, Ryan. Okay, no issue already, Good. Yeah, that's what I going to expect you guys to do. Oh, Kunwei, good. Luckily, you guys, this time the final exam is going to be physical, right? I'm not sure it's good or not, this semester. I'm still wondering the midterm, yeah, if it's online, it's going to be Simulink based. Then I happily, I can actually see who can do it, who cannot do it usually. And those copies of friend one, I wish you all good luck. Like I say, Simulink can never be exactly the same. And I'm very sure that the friend that you submit will not put in effort to even change it for you. So you prepare to share your mark. Don't say, so I'm the one who do everything. Why am my mark and my friend same? So I have to really warn you guys here. Once I spotted two exactly, I just divided by 2 Unless you are so confident you can score over 20 over, and you're willing to share your another 10 marks to help your friend who is going to score 1 or 2 marks. Okay, that is entirely up to you. Okay, good. You see, the first round, right, it takes a bit of time because you are unfamiliar with many things. But once you get the basic done, right, the second round you can see is literally less than 5 minutes, and you build from what you have done. Remember, you cannot wait until say, okay, today I feel much more, maybe sometimes I know that you don't feel like doing it when in the class. It's okay, but make sure you go home, watch my video, and practice it. Okay, so because like I said, knowledge is building up. You cannot say, okay, I wait until week 8, okay, I feel got mood and start. I tell you, it's too late already. It's too late already because knowledge is cumulative. It's not like suddenly, okay, week 14, I start to do it, you jump, no way, right? And I'm not going to answer you guys whatever I already explained in the class. Don't ask like, no, in week 10, sir, where to find the RMS plot? I say, eat yourself. Sir, why the format not correct? I also say, eat yourself. There is a reason why sometimes I really be very reluctant, right? Especially week 13, week 14, suddenly got student wow, so enthusiastic, come to the office and ask me about, hey, sir, how do I calculate the thermal resistance, or how do I model the thermal resistance, you know? I will just tell you, sorry, I also forgotten already. Okay. Tê Vun Hong, Nicholas, okay, very good. Phong Thung Hao. Phong Chun Wei. Okay, make sure you all save this one because the coming one, okay, will be based on this full bridge. If you don't practice the previous half bridge, it's fine. Make sure you do the full bridge because this is the foundation, okay, the foundation of everything. Now you can see you don't need even a capacitor, but you already can produce the waveform, okay? You can produce the waveform. Okay, like I said, just make sure you do that because if you look at my slide, right, after I talk about modulation, you see the rest is all based on this already. Okay, after the modulation, I will still based on this one. Just make sure this set of full bridge is in a working condition. And then when I further move on, I will skip this one because we are not going to make any hardware. But if we got time, after I finish all the chapter, I can come back here. Okay, this one is for when the assignment of physical class, they are hardware, you know, you can, how do you use Arduino to program this complicated thing? Okay, how to do that? Okay, and then how do you program, and then you can actually produce the PWM. It's all captured in the scope, proven can work. And then how do you connect to make your real hardware? Okay, and then yeah, we will talk about the application. Okay, anyway, still got half an hour. Let me just go through because otherwise I also worry not enough time to finish everything. Okay, up to now, we already understand that how to use half bridge and full bridge to actually generate an AC output. Okay, the question again, we will have a very high harmonic. All right. Then to solve this problem, we need to introduce a modulation. Okay, so this type of modulation, there are actually a few types. Okay, the two commonly used, one is this one, where you can see in most of the commercial inverter. Okay, it's called SPWM, sinusoidal pulse width modulation. Now in MATLAB, okay, it's quite easy because they already have a block for you to do that. Okay, so it saves a lot of time. Okay, but I will still explain the principle. Now, when you have the SPWM modulation, you will be able to produce a sine wave output. That's the key. Okay, without any modulation, there is no way you can produce a sine wave. The sine wave you produce even can be as less than 1% of THD, which you can connect it to the grid already. DMV or whatever utility, they don't The purpose of using this, of doing this, is to reduce the harmonic, okay? Remember I said harmonic will cause overheating on any load that is inductive load. And then, of course, a reference signal is required. Now, we have this SPWM block, and this is our reference. Our reference has to be sine wave, right? Because you want to modulate the sine wave, right? Then the sine wave, after you modulate, okay, this will be the P will be the output. And this output, right, is not a single output. It is a 4 output. Why 4? Because our bridge got 4 transistors. Okay? So you will generate 4 different output. And these 4 output, like I said, the basic is that these two will never turn on at the same time. Now, when we modulate them, the frequency of modulation is increased. It's not, this one is 50 Hertz. Our reference have to be 50 or 60 lah. But after we do go to this SPWM, easily you can have like 5 to 20K of switching frequency. Okay, kilohertz. All right, so it's actually chopping the whole sine wave into small pieces. Okay, so that you will need a high frequency. Now, the most commonly used in the commercial IC is around 20. Okay, 20 kilohertz, which is really good enough to suppress all those harmonic and good enough to even drive a AC motor already. And this gain is basically because the output here is only 1 volt. 1 volt cannot turn on your transistor. Your transistor threshold voltage is depend like I say, it can be 2, it can be 3, 4, right? Depend on the data sheet you use. To play safe, I usually put 5. Okay, and then we will have a 4 output here, but we want to split them. So there is what we call a demultiplexer here. A demultiplexer to split them into 4. So these are all connected to the transistor. So I just show one of them. Okay, and I show the input of a sine wave. So what happened is that, okay, these are the setting of the 2-level, okay, SPWM, all right, and then the sine wave, okay, the reference sine wave. And what happened is that when the output, right, you can see this is my input of my sine wave, right, and this is the output of the modulator. Now the difference is that the higher the amplitude, right, the wider the duty cycle. And when it go to negative, right, you can see the duty cycle become very short, right? It's fine. So it modulate, it change the duty cycle, wide, close, wide, close. Okay, so this is how the modulation take place. Now, this one is to make you all see it. That's why the frequency is only 500 Hertz. At least 10 times of your frequency. But in actual application, at least 5K to 20K. Now, never mind, let us do this first. Because you need this one. Okay, you need this one in order to see this, you see? In order to see this output, the 4, to connect to them. Okay, you need to see this. Okay, now let us create this one. Okay, let's do it together because I don't have any of this model with me. Okay. Oops. Okay, come. Let's do it together here. First of all, you need to know where is the SPWM, right? Okay, it's in Simscape again, electrical. If I'm not mistaken, it's under the specialized power system. Under specialized power system control. Okay, see got or not? If no, it's somewhere else. Control, not inside control. Oh, sorry, power electronic. Power electronic control. You see, because this SPWM is for power electronic. So inside power electronic control, you see, PWM generator, 2 level. What we have been using all the while is a very fundamental, okay, PWM generator. This is 2 level because it's AC, got positive and negative. Okay, so now we have this one. Okay, and then we can go back to the fundamental, this what we call this Simulink. Okay, you only need this block in the power electronic control. Okay, so we will have a source. Okay, you find sine wave as a source. Okay, you can create a sine wave here. And then, okay, we just put another scope. Okay, and remember I already teach you all how to make the scope to display, right? Okay, you go to setting, set to layout, 1, 2, click, apply, okay. Okay, then you will have a 2 display. Okay, then after that, now we need to have a demultiplexer, remember? The demultiplexer to split the 4 signal. So that one will be under the common use block, demultiplexer. Drag it over. Now the demultiplexer only got 2 output. How to make it 4? Double click, change to 4. And then okay, it becomes 4. So it split out the 4 signal into 4 independent lines instead of putting them together. Okay. All right. So when you have these 4, now you just need to connect them together, connect them together, connect them together, and then connect here. Okay. Don't forget to change your time, 0.1 or 0.02 for 1 cycle, depend. Let me try here. For 1 cycle, then okay, before that, I think we need to do some changes. Magnitude, okay, okay, 1. Frequency is 2 by 50 Hertz, right? Okay, 1 over 2 by, is it 2 by 50? Sorry, I think I typed wrong already. Okay, phase, I think it's okay, no need to change, just double check first. Yeah, 2 by 50, okay. Oh, yeah. Okay, 2 by 50, correct. And then these 2 level, okay, these 2 level important, this part you all must see. Remember, we need to multiply the frequency, right? You have to multiply correctly, Now here you see frequency. This frequency is not the frequency of your 50 Hertz. It's this SPWM switching frequency. The switching frequency is the multiplication of your grid frequency. For example, our grid frequency is 50 Hertz. So you multiply by 2, 3, 4, 5, 6. You don't suddenly put 120 something very odd, then your inverter will have problem. So in this case, we just try to make things simple. We put 500 or 50 Hertz times 10. You want to make yourself more clear. Okay, you just do something like that. The rest should be okay. I think nothing much to change. 4 volts? Oh, yes. Oh, Ryan, you're damn good. Yes. Because you had to tell the SPWM how many, you see, we got single phase, half bridge, full bridge, and 3-phase 6 pulse. Scary eh? Later, usually final outcome are the most difficult one. So again, it looks like most difficult, but if you start to do my half bridge, it just copy another bridge, that's all. So simple, can finish in 5 minutes, guaranteed. Okay, so let's run. All right, no error. Oh, you see, beautiful, right? Now, if you want to see all 4, right, also can. You just need to make your scope, let's say you want to see all 4. Okay, before that, I think we try to play around with this one first. 500, right? So if you increase the frequency, what will happen? Okay, let's say I put it 20 times, double out the frequency, 1000. You can see that it become, more. You can see that the pulse, right, become more high resolution. The higher the frequency you go, the more high resolution is it. And that resolution is just like your camera, how many megapixel. So the megapixel higher means that clarity, so the sine wave more smooth. When the sine wave is smooth, there's no harmonic. But of course, you don't like say, well, I go infinity. No way, okay? The Nyquist sampling rule are there to govern this. Okay. So come, just play around and show me. Because again, this is a very important piece of modulation. If you want to see more, right, like I say, okay, I show you, you just put more output you put 5, right? You want to see all 4, you will see they are different. Then 1, 2, 3, 4, 5, okay? Then you can see all 5. Okay, all 5 here. Then let's just make it back to 500 so that you can see the difference easier. Okay, then of course you can resize your scope make it nice Okay, 1, 2, 3, 4, 5. So when you run this, then you will be able to see all 5 of them. You see, none of them, right, will turn on at the same time. Remember to save this one because you're going to use it for a further modulation. And of course, after Chinese New Year, we will come back how to calculate them. Very important because, I used to set this type of question. Okay, you see, the thing is that power electronic is not I myself really want to create a question that want to fail you all. Because they are always interrelated. Remember the switching loss thing? If you got in the middle, you got one step wrong, that's it, So you have to be very careful. Same for this one. If you have one step wrong, right, again, the rest is gone. Okay? So my advice is like, you have to do a bit of practice. Okay, come, let's show me in the, whatever you have done. I believe this one should be easier, right? Oh, see? Wow, so fast, good. Wow. Ryan, try to do the 5 display, see can or not? Someone, Matthew. Okay, good. Make sure you all save this because you're going to use it again. Wow. Okay, almost 6:30 already. Oh my goodness. Yes? What is that?
My layout, right? For my layout, right, the scope there, right, I only maximum break until 4 column only.
Good question. Okay. Our friend online say he can only set up to 4, cannot set up to 5. Anyone have this problem here? If you never try, you never know, I tell you. Can I? Okay. Now, the key challenge is that it only shows 4, right? But, oh, cannot all. Very simple. You press, move, you can move how many also can lah. That's the trick. Okay, you have to hold and press drag. Try it.
Okay, then can, sir.
Can or not?
Yeah, can.
Ah. You see, you all don't underestimate the class I giving you all here to do online. Because this is really you have to do, only you can know. That's why I really sometimes, I have been very honest. If you want to come and ask me question, you better confirm it's never asked in the class. I'm sure in the assignment, some of the guys will say, hey, sir, I only can do 4. How come get a 5? Really, I give them middle finger if I don't want to speak anything. You see the purpose, every moment has a purpose here. It's not that ask you all to do, I sit here, relax, right? No, over 100 slides, I need to explain, okay? Okay, really, now, okay, almost 10 minutes to 6:30. I think we will stop here today because after doing this, right, you will see that the next part, I'm going to explain, okay, I'm going to explain how to calculate the duty cycle, you see, step by step, okay, with the equations. Okay, we're going to do that after the Chinese New Year. Okay, we are going to calculate them step by step. Okay, you will see the difference. Of course, I'm not going to do all. I calculate 3 steps, the process is repeated. Okay, and then, okay, I will explain how the secret of this box inside. You can actually create it, the same thing by using all this. Okay, like I said, if one day you were asked to do whatever modulation and again, the software that you use does not have the same block. So you can create your own. Okay, and then, yeah, after that, we're going to use a SPWM to connect to the full bridge. And then you will have something like that as an output. And this is already good enough to use for AC motor drive. The industrial AC motor drive are all like that. They no need to have filter because the motor itself is already inductive. So it acts as a filter itself. Okay. All right. So yeah. Okay, good. I'm very happy to see that at least, yeah, many of you take part in this simulating exercise. Okay, so you will know the pattern and then okay, so any questions before we end the class today?
Sir.
Yes.
You said before last time, right? In DC motor, right, they need like a diode for the flywheel, right? For AC, no need.
Or AC no need. That one is only for DC motor.
Oh, okay.
Okay, my battery only left 22%. Okay lah, but I think today is good enough lah. It's not very heavy. I think it's quite lightweight lah for today's class, right? We just talked about half bridge, full bridge, and simulation. And when you, like I say, when you master this full bridge, right? 3-phase is just a piece of cake lah. Okay, because I also cover 3-phase here at a very later, what we call this you see, this is 3-phase. You see, three-phase, there is no half bridge or whatever, there's only full bridge. So you just copy and paste and put another set, that's all. Okay, but of course, you start from scratch, you will start to see a lot of error lah. Okay, so I will also cover three-phase. At the end, you have to do this, three-phase, okay? And it getting more complicated lah at the end. You know, we even talk about Tesla Model S, motor control. Don't worry, you know, Nissan Leaf, you all can be, you know, design all this. The train system also got, but I have to stop somewhere here because if I continue, cannot finish the other two. You see, we got 4 converter, right? This is only one of them, you know, and almost half of the semester gone already. I also like, oh shit. But it's good thing lah, think it positively. The less I teach, right, the less question I can come out. Right, if I think so much question, how are you going to memorize? And bear in mind, this one is physical. Okay, so yeah. So if you don't have any questions, I think we can end the class today lah. Okay, and then I will see you again. Okay, after Chinese New Year. Okay, for those I think most of the Chinese already in front of the renewal dinner table already lah. Okay. Yes.
I haven't scanned the QR code for physical class.
Wait, don't kanchiong.